on some examples. I've written the integration rule that I think is the trickiest in this section, which is that if you want to integrate x to some power, then you should add 1 to the power to undo what differentiation did, and then divide by the new power. So this is how we will undo this process of differentiation. In other words, the integral of x to the n is x to the n plus 1 divided by n plus 1, and we're always going to include this constant of integration. So usually your last step when finding an indefinite integral like this is just to add c, that constant of integration. In a later section, we'll talk about what a definite integral is, but for now, you should just think of the indefinite integral as meaning take an antiderivative. And for that, we're just going to use that system of rules that we saw a second ago. So now let's integrate 2 dx. So 2 is secretly a multiple of a power of x. Remember that we can think of this as 2 times x to the 0th power, because anything to the 0th power is just 1. So that's just a goofy way of writing 2 times 1. Okay, so we can follow our rule up above. The rule says that if you want to find the antiderivative of something like this, first of all, notice that I have this constant sitting out front. So I can take the constant outside of the integral. So that would be 2 times the integral of x to the 0th power dx. And now what I can do is I can use the rule at the top of this page to say that if I want to integrate x to the 0th power, what I should do is I should take that power and add 1 to it. So the new power would be 1. And then I should divide by that new power. So that's what I get here. So notice that 2 is being multiplied by this integral here. So I should still have a factor of 2 sitting outside. But this can be simplified to 2x. And usually as our last step, what we would do is we would write a plus c here. Because really in all of these steps, I should have a constant of integration that I can add anywhere that I'd like. That won't affect the derivative. So what we should get as our answer here is 2x plus c. Notice that you can just memorize this sort of result without going through all of this power stuff. So as you start to get comfortable with this, I would expect you to just remember that if you want the antiderivative of 2, it should look like a 2x. That's the function whose derivative would be 2, and then we know that we also have to add a plus c at the end. So you don't necessarily have to go through all of this reasoning. I just wanted to demonstrate that you can use this power rule here. Next, we'll look at the antiderivative of 16e to the t with respect to t. So remember, we're integrating this thing, 16e to the t, and these outer two symbols, the integral symbol and the dt, are just telling us that we want to find an antiderivative of the underlined thing with respect to t. So we want to find an expression so that if I take a derivative with respect to t, then I'll get 16e to the t. Just like in this example, if I take a derivative of 2x plus 7 or 2x plus 12 or whatever, I would get the underlined expression here, 2. So if we wanted to integrate 16e to the t, then again what we can do is we can take that constant factor out. So this would be 16 times the integral of e to the t dt. And now we want to undo differentiation of e to the t. But remember that differentiation of e to the t, or rather I should say the derivative of e to the t, is just e to the t. So similarly, the integral, or if we undo that process, of e to the t is going to be e to the t. So this will be 16 e to the t. And remember, we should have this constant of integration in all of these. So we'll have 16e to the t plus c. And you can check that if you take a derivative of any function of this form, you'll get 16e to the t. Okay, so this is similar to that first example. Now we're going to get to use the product rule a little more carefully. So here I would first take out that factor of 3. Just like with differentiation, you can pull out these constant factors. They just hang out. So this would be 3 times the integral of x to the 4th dx. And now the thing that we're trying to integrate is an x to the 4th. So we should add 1 to the power and then divide by the new power. So we'll get that. and we'll have a plus c. You can leave it in this form if you'd like. Some people like to combine the fractional parts, so we get a 3/5 times x to the 5th plus c. That's an equivalent expression. So either of these would be fine. But either way, what you should do is whenever you're integrating a power of x, you add 1 to the power and then divide by the new power. So now we'll apply that a few times down here. Notice that there are 3 separate terms here. So if I wanted to integrate an expression like this, what I can do is I can break this up into the integral of all of these terms separately. So this would be the integral of the first term minus the integral of the second term plus the integral of that third term. And the reason that I can do this is that I can do the same thing for differentiation. In other words, differentiation applies term-wise, so if you undo a process that applies term-wise, then you can do the inverse process term-wise. So I can integrate each of these terms separately. So if I try integrating this first term, what I would probably do is factor out the 2, and then similarly I'll factor out the 3 from the second term. From the last term, there's nothing that I need to factor out, so I'll just leave it as an integral of 1 dx. And now we'll start applying our power rules. So we know that for this first expression, we'll need to increment the power by 1 and then divide by the new power. And we'll do the same thing over here. So if I change that 2 to a 3, then I'll divide by the new power. And then over here, the integral of 1, we're looking for a function whose derivative is 1. The function whose derivative is 1 is x up to a constant. So we would also need to add a constant. Now, you could add a separate constant for all 3 of these. So you could have like plus c1, plus c2, plus c3. But because all of those are just unknown numbers, it's easiest to just combine all of them into a single constant c. So you could have 3 separate constants, but saying that you're adding 3 unknown numbers is the same thing as saying that you're adding some unknown number. So it's best to usually just put a single c here. Okay, and then if you'd like, you can clean up this expression. I would be happy with an answer like this, but notice that, for example, you can cancel these 3's. You can cancel a factor of 2 here. So I could write this as, for example, 1/3 x to the 6th minus x cubed plus x plus c. That'd be sort of a cleaner way of writing the same antiderivative. So that's what we get as our antiderivative here. Okay, now let's do maybe a couple more. I'll do this second page. So here we're integrating, and by the way, as you start to get comfortable with these, it's okay to start skipping steps. So whenever I integrate something like 7x squared, I don't usually write the step where I factor out the 7. I just remember that the 7 is along for the ride, and then I'll integrate x squared in my head. So maybe let me write that down. So if you need to integrate something like 7x squared, you don't have to write the extra step where you factor out the 7. You can just factor out the 7 mentally, and then integrate an x squared, which would give you an x cubed over 3, because you increment the power by 1 and then divide by the new power. So you don't have to keep writing all of these intermediate steps as you get comfortable with the process. So here we have an integral of 5 over x minus an integral of 4e to the x, because we're splitting up into these 2 separate pieces, and I'll keep writing the little dx. If you'd like to abbreviate by leaving off the dx, so if it's clear that your function is just a function of a single variable like x, it's okay with me if you suppress the dx. So you don't have to always write the dx, but I'll try to remember to in this video. Later I'll probably suppress it, because usually it's clear which variable you're integrating with respect to. So for this first term, what we have is I can factor out a 5, and then I would have the integral of 1 over x dx. And then similarly for the second term, I can factor out a 4, and I'd have e to the x dx. Now, the thing whose derivative is 1 over x would be ln. So this would be 5 times ln x. The technical thing to do here is to take the absolute value of the x, because it's okay to integrate 1 over x where x is negative, you would just need absolute value signs to make sure that you're taking ln of a positive number. So the technical answer is this one. I'm not going to penalize you for just putting an ordinary ln x, though. So it would be okay to just put ln of x like we normally do. And then when you integrate e to the x, it remains e to the x. So you would get that. And then remember that when we take the antiderivative, we'll have a plus c, this arbitrary constant of integration outside. Next, we'll look at this one. Here we're applying the same rules, it's just that this time the powers are a little bit more complicated. So this first expression I could rewrite as a 2 times the antiderivative of x to the 2/3 minus a 3 times the antiderivative of 1 over x to the 4th dx. And for both of these, I want to apply the power rule, but it's going to be a little bit tricky to do that because these powers are a little bit messy. So for this first one, I'm just going to leave this expression alone. But notice that this second term, I have a 1 over x to the 4th, which could be rewritten as an x to the negative 4. So we're going to do the same sort of trick that we did for differentiating expressions like this. I can rewrite that x in the numerator with a negative power. But now I can apply the rules that we've been using. So I'm going to take the old power of x and add 1. And then I'll divide by that new power. So if you'd like, you can just actually compute this 2/3 plus 1. That would be 5/3. So you would be dividing down here by 5/3. And all of this is in the exponent. So that's an x to the 5/3. And then the second term here is going to be a minus a 3 times, now if we take negative 4 and add 1, it would become a negative 3. So we'll have a negative 3 here, and we divide by the new power. And now we can clean this up a little bit. So here we have negative 3's that cancel. So I can write this first expression as a 2 times x to the 5/3 divided by a 5/3. And then I'll have a plus x to the negative 3. Because I can cancel these negatives to get a plus sign and cancel the 3's. And then if you'd like to clean this up even further, you can. So this would all have a plus c with it. But here, whenever you divide by a fraction, remember that's the same thing as multiplying by its reciprocal. So we could also write the same expression as a 6x to the 5/3 divided by 5 plus a 1 over x cubed plus c, if we'd like. So that's sort of the cleaned up version of that one. We're going to have to do a similar power trick for this last problem. So notice that here I can pull out that factor of 4. Again, you don't have to write this step if you're comfortable just remembering that your antiderivative will be multiplied by 4. So you can just keep that 4 along for the ride. The trick again is to rewrite this so that we can use the power rule. So I'm going to write our variable to the 3/5 power, because remember that taking a 5th root is the same thing as having a fractional power with 5 in the denominator. So these are the same thing. And now we can do the same thing that we did in the previous problem. What we should do is we should add 1 to that exponent. So 3/5 plus 1, or 3/5 plus 5/5 would be 8/5. So that's the new power, and we divide by the new power. And then we'll still have a plus c here. So this would be an acceptable answer. If you want to clean this up a little bit, you can. This would be a 4 times 5 times w to the 8/5 divided by 8, because dividing by 8/5 is the same thing as multiplying by the reciprocal 5/8. So we would get this, and then we can cancel these common factors. So I can cancel a common factor of 4 to get a 5w to the 8/5 divided by 2 plus c. So any of these expressions would be fine. Okay, and then in our next video, we'll continue